Anybody here that I owe homework to? I'm handing back the expected value homework 2. Okay, we ready to go? All right. Homework 3, the dumb exercise, is due on Thursday. This is Tuesday. So this is your chance to ask questions about that. Any questions?
So everybody's done it? This homework is time-consuming. And I'm kind of jammed up here for time because next Tuesday is a holiday. It's Veterans Day, so we don't have any class next Tuesday. So that means that we lose half a week. And then right after that, we got Thanksgiving coming up and all kinds of other stuff at the end. So I thought what I'd do is I'll make this homework is due on Thursday, but I'm willing to accept it late in the following sense. I'll grade them over the weekends. So if you can get the homework to my office by Saturday, I don't know how you can do that. You can certainly get it in on Friday. If you get it in on Saturday, I'll come to my office on Saturday afternoon and pick up whatever homeworks are there. So if you can get them in my mailbox or slip them under my door, that'll be okay. After that, if they come in later than that, then I might take off credit for being late. Okay, does this make sense? So in other words, I'm giving you a little bit extra time, but I can't give you till next Tuesday. There is no class on Tuesday. Also, I want to get into homework 4, which I'm going to start discussing today. So you should download that from the website, and that'll be due a week later. And homework 4 is basically, it is a continuation of homework 3. It's very similar to it, and in fact, it's easier because it's there's one new part, which involves convolution, but there are no graphs. And most of it's the same as what you did before anyhow, so homework 4 should be relatively easy in terms of the amount of time it takes to do it. But I'll discuss that soon. Okay, so I have homework 2 to give back. So let's say who's here? Rambarath. Let's see who else. Khalil, Chalut, Lambro, Gosin, Machiavello, Blazon, Mitchell, Valius. I think that's it. Anybody here who I owe homework to? Khalil. That's Khalil.
Yeah, I knew that couldn't be me.
Okay, you're...
Stefan. Should be in.
Yeah, you're in here. Okay, Lenoff, Ward, Farber, Valenides, Mueller, Stefanoff, Tomasello, Ambrine, Alvarez, Stewart, Yakovos, Bartholomew, Patel. Okay, so homework 3. Technically it's due Thursday, and looks like this. First there was this code, and what you were doing is you're going to generate 10,000 values. So for I equals 1 to 10,000. Of course, this is in BASIC, you don't have to use this language. And then you're going to generate X. So this is the new big deal here. You've got this, imagine you have this urn with these tickets in it, and you reach into the urn, you pull out a ticket, and the contents of the urn are what's specified by the description of the random variable. That is, its distribution function or density function or probability mass function or name, as the case may be. And then, once you calculate the X, statement number 200, let me give myself some room here because I'm going to add something. So statement number 200 says you're going to accumulate the X's. And accumulate them in something called X1, for example, S1. So when you get done going through this loop 10,000 times, you're going to have some 10,000 values of the x's that are sampled from that urn. And then for statement number 300, you're going to accumulate the sum of the squares of those things. And this is so you can calculate the mean, this is so you can calculate the variance. And then there was a statement 400, which I'll write this way. If something or other, and all this did was ask whether or not the value of x you calculate was less than or equal to a half, and then it would take that number of x's, divide by 10,000, and that would give you the probability that x is less than a half. But that was only here for the illustration of writing the code, and not because it's something I'm asking you to do. So what you had to do is you had to change this instruction to calculate. In fact, it was the probability, so let me write it that way. If x was greater than, what was it, 0.25?
Yes.
Okay, so if it was greater than 0.25 and it was less or equal to 1.35, so we wanted to calculate the probability that x lies in the region between 0.25 and 1.35. So if it meets that condition, then you're going to count it. So then c equals c plus 1. And at the end, you're going to divide this c by 10,000. That gives you the probability that x lies in this region. And then statement number 500 is next I. In other words, it just delineates the loop. And then you're asked to print the answers. So what you want to print is you want to print S1 divided by 10,000. And that, of course, here's S1, so that's the sum of all the x's divided by 10,000. That's the average x, or in other words, it's the value that would be the expected value if in principle. So this then corresponds to the expected value of x. Then you want to get the variance of x. To get the variance of x, you take the average of the square, so that would be S2 divided by 10,000. And you want to subtract from that the square of the average. So that would be S1 divided by 10,000 squared. And then you want to calculate the fraction of x's that lie in this region. So that would simply be C divided by 10,000. And the big deal here, the new thing, was that when you generated the x's, you had to use the inverse transform method. And there were 4 cases for the x's. So let me write down what they were. Case 1, where x is uniform 0, 1. And this one is actually a test of the random number generator, as I explained. Because the random number generator is supposed to give you values that are uniform between 0 and 1. So if this one works, that means that the random number generator works. And if the random number generator works, then all the rest of them must work, because we proved that the inverse transform method will do what you want it to do if the random number generator generated numbers that are uniform between 0 and 1. The second case was the case of the exponential. So in this case, we could say, although this isn't the notation I used, that x is exponential, and the value of lambda was 2. The parameter was 2. The third case was that of a constant. We simply said that the probability that x equals 1/2 is equal to 1. So that means that x takes the value 1/2 all the time. And the fourth case was a discrete random variable in which the random variable x takes 2 values. The probability that x takes the value minus, was it 0.2? Was equal to 1/2. And the probability that x takes the value plus 1.2 was equal to 1/2. Okay, so that's where we stand. In addition, I asked you to calculate the distribution function. And the distribution function corresponded to the values that the fraction of x's that are less than t for various specified values of t. That's what's given in the table in the bottom half of the page of the handout, of the homework assignment. And then what you're supposed to do is you're supposed to plot those values against the theoretical distribution function. And of course, if everything works, then the simulation values and the theory values should be close to each other. And the only, I shouldn't say difficult one, but the only one that required maybe a little bit of work, and I did this, let's see, I did this in class, so let me find out. Yeah, the exponential. Okay. So if x is exponential with parameter lambda, I proved in class that the instruction that you would write would be x equals minus, now you need 1 over lambda. Well, let's see, first I'll write it in theory. It's equal to minus 1 over lambda times a natural log of 1 minus a random number that's uniform between 0 and 1, which means that in a code, at least in BASIC, it's x equals minus. In our case, lambda is 2, so I'll write it as minus 1 over 2 times, and natural log in BASIC is log, and the random number is rnd. And this is actually derived in the book. This is on page 477, where it's given as an illustration of the inverse transform method. Okay, so this is what I did last time. Now, the next step, well, before that, are there any questions about this? This is now, remember, this is homework 3, due Thursday. I'll accept it late. We have no class next Tuesday. So it's best if you hand it in on Thursday. It's next best if you hand it in on Friday, that is, come to my office or put it in my mailbox. I'm going to come to my office on Saturday and pick things up and grade them on Sunday. So if you can get it to my office on Saturday, that's okay. But I don't know for sure whether or not there's a place to put it. I suppose you can slip it under the door if it's not too thick, and if there's not a whole bunch of them piled up there. So everybody okay on homework 3? Any questions about that? How many people did it? Okay, and it worked out?
One case. We're working on the last case.
Okay, but everything you did so far works out?
Yeah.
Okay, so I'm telling the truth, right?
Yeah.
Okay. All right, so now the next step is to say, suppose that when we sample from this urn, instead of generating 1x, we generate 2x's and we add them up. Okay, so now I want to talk about addition of random variables. So for example, this is what we've done in the past. Let me erase this. Go back to the dice problem. And you have 2 dice, which I'll call x1 and x2. And x1 can take the values 1, 2, 3, 4, 5, 6. And x2 can take the values 1, 2, 3, 4, 5, 6. So the points in the sample space correspond to those cross points right there. And when you roll the dice, what you're doing is you are adding up the 2 random variables, which are the face values of die 1 and the face values of die 2. So y, which I'll define as x1 plus x2, that's the value of a roll of 2 dice. So we've actually looked at this idea of adding up random variables, but we haven't been very rigorous about it because it was unnecessary, because you could see exactly what was going on. But for example, suppose I wanted to calculate, for example, what's the probability that the sum of the 2 dice equals 8, let's say. Okay, so 8, that corresponds to 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. So what we did was we counted the points in the sample space, 1, 2, 3, 4, 5, divided by the probability, by the number of points in the sample space, which is 36, so we know the answer is 5 over 36. But what you're actually doing there is, in fact, you're adding things up. What you're doing is you're adding the sum of the probability that x1 takes the value j, let's say, and x2 takes the value 8 minus j, summed over all j, from 2 to 6. Because when j is equal to 2, then you're calculating the probability that x1 is equal to 2 and x2 is equal to 8 minus 2, or 6. That's this point here. That probability is 1 over 36. When j is equal to 3, you have the probability of this point. When j is equal to 4, this point, and so forth. Now, furthermore, if the events are independent, which we usually assume here, in fact, we showed that if all the points are equally likely in this case, then what that means is that the probability or the events must be independent. The dice must be independent. So by independence, instead of writing each of these as 1 over 36, we could write it this way. It's the sum as j runs from 2 to 6 of the product of the probability that x1 is equal to j times the probability that x2 is equal to 8 minus j. Of course, this is 1/6 and this is 1/6, so their product is still 1 over 36, so it's the same answer, but I wanted to write it in this form, and this, of course, is 5 over 36 when you get done with all the arithmetic. So we've done this already a zillion times from different points of view. Now, look at this thing right here. What you have here is you have a sum of products. And in that sum of products, there's an argument, which is j. And you see that as j varies, this value plus that value, j plus 8 minus j, adds up to 8. And as j runs from 2 to 6, the sum of these two values always adds up to 8, and that's exactly the value that's given here. And so that's called a convolution. Convolution is just the name, which corresponds to a sum of products in which the arguments of the products add up to a constant. And it appears in lots of branches of mathematics and engineering, and so this is just one of the applications of it in probability. So it turns out that if I want to calculate the probability mass function of the sum of independent random variables, that the arithmetic that's involved is what's called a convolution. Now, suppose that instead of rolling 2 dice, suppose I ask this question. Suppose that I took this as an example. Here's my spinner here. So this is the value 0, and this is the value 1. And now what I'm going to do is I'm going to spin this twice. That is, the first time I do it, that's x1. The second time I do it, that's x2. I want to add them up. In fact, if you think about it, if you look at your past education in arithmetic, what you do is you learn about numbers, and then the first thing you do once you understand what numbers are is you take operations on numbers, and the simplest operation is simply addition. And once you understand addition, of course, everything else in a sense really comes from that. So if we can understand addition, then we're home free. So everything you've done in the past with deterministic numbers could be done with numbers that are random variables. And of course, addition is the simplest possible case of that. So of course, if I'm adding up two numbers that are random, then their sum is random. But they don't have to be discrete dice. They can be anything. I can add up any random variables I want, and it doesn't have to be just 2 of them. And if the random variables that I'm adding up are random, obviously they are if they're called random variables, then the sum is a random variable. And the question is, how do I find the probability statement or distribution function or probability mass function that describes the random characteristics of the sum of the random variables? Okay, so we've already done that here in this case, but this is a special case. So now what I want to do is I want to go back to homework 3 and I want to make it homework 4, and now I'm going to change it slightly so that instead of generating x, you're going to generate x twice. Add them up and put them in the same code. So this is almost the same thing as before, except that the theoretical analysis is different. And this is very important because, as I say, if you're going to do any work with random variables in an applied sense, then the first thing you're going to do is add them up. That involves convolution, and this leads to what's called the central limit theorem. It's the key to the central limit theorem, which is very important. And that and other things, all this comes together at the end to give the example, the queuing example that I want to give, which puts all of this stuff together and puts it into an actual engineering example where you're concerned with the performance of a system in which the thing that drives the system is a complicated thing with lots of random variables with different distributions, and somehow or other you can work it out and still predict the performance of something that's complicated. Okay, so that's where we're going, so we have to understand this convolution stuff, or sums of independent random variables. So let me go to homework 4. Okay, so here's what homework 4 is. So it's the dumb exercise continued. So we're going to do the same thing, but we're going to sample from 2 urns. So you're going to do 10,000 values, but instead of generating x, it's now going to say generate x1 and x2. And there are going to be 4 different cases. Now, the first case is going to be the same, second case is going to be the same. So whatever expression you use to generate x1 here, which is simply RND, or here, which was minus 1/2 times the log of 1 minus RND, whatever you use there, you use here and here. You do the same thing twice. But remember that you have to use different random numbers because otherwise the values will not be independent of each other. So don't try and be efficient and define a numerical value, a specific value for the random number, and then use that same random number twice. So for example, when I wanted to generate x1 and x2, I could say x1 equals RND, x2 equals RND. Because in the computer, when it sees RND, it just takes the next number in the random number sequence. So these are supposed to be independent numbers. Okay, same thing here. We'll get to the last 2 in a moment. And then what I have to do is I have to now take the new values of x that I got, you put in a new instruction, and I'll generate y. And y is equal to x1 plus x2. So if you can generate the x's, you just do the x twice. In other words, you sample from the urn twice, you add them up, and you call that y. And now we're going to do exactly the same thing with the y's that we did with the x's. Except that, of course, the y's are now the sum of the x's. So with the simulation, it doesn't care. So all that happens is, in the code, I'll change this value x to y. And I'll change this x to y. And I'll change this x to y. And then it's exactly the same thing. Okay, so in homework 4, the code looks like that. Now, you're going to do it with 4 cases, 2 of which are exactly the same. In fact, 3 of which are exactly the same. So this is going to be the same, this is going to be the same, this is going to be the same. Of course, the theory is going to be different now, but not that much different. This one's going to be different. The reason I want to make this one different is there's no point in considering this case again, because if x is a constant, then when I add up 2 of them, it's still a constant, so nothing changes. So I'm going to get rid of this one, and I'm going to replace it with something that's new. So this is one of the new pieces in homework 4. And by the way, I'm not asking you to compute the distribution function graph, so that means that in terms of the amount of time it takes to do this, it's much less. If you know what you're doing, you can do this in an instant. Of course, if you don't know what you're doing, take more than an instant. But with homework 3, it takes time whether you know what you're doing or not, because you actually got to plot graphs, and that's kind of annoying. Okay, so now here's case number 3, and it is the following. Now I'm going to give you a new density function. The density function looks like this. It's 0 when t is negative. It's 2 minus 2t when t lies between 0 and 1. And it's 0 when t is greater than 1. So this is a density function that I just made up for no reason. Not for no reason, but essentially, I just made it up. And so one of the things you have to do here is when you generate the x's, Now you're going to have to apply the inverse transform method to a new random variable, which of course is part of the point, because if the only ones you ever do are the ones that I give you in homework 3, then that's like saying that you learned how to add, but you only learned how to add 2 numbers. Any other case you didn't know how to do. So you have to be able to generate random variable values from any population. So now I'm picking another one. Because remember, on the final exam, the same thing's going to happen. I'm going to give you some random variable, and I'm going to ask you to write code in BASIC or whatever pseudocode you want that will correspond to the statement in the homework that says generate the X. Okay, so you have to understand how the inverse transform method works. Now, the other thing is that in case number 3, instead of doing from this twice, what I'm asking you to do is to add, that is, imagine that you now have 2 different X's. So you have 2 earns here. So this is earn X1, and then there's another earn X2. And so for case number 3, where it says generate X1, use the instruction that generates that, which is simply X equals R and D. And for X2, you use the inverse transform method to generate something from that. And you add those 2 together. So this time what you're doing is you're picking a value from here, picking a value from here, and otherwise everything else is the same. Once the X1 and X2 are known and combined to make a Y, the rest of it is exactly the same as it was before. Okay, now what's this density function here? Let's see, I guess I can erase this. In case number 1, the density function looks like this. Here's 0, here's 1, here's 1, that's the density function. In case number 3, the density function looks like this. Here's 0, here's 1, and this is just a triangle. When t is equal to 0, f has the value 2, and then when t is equal to 1, f will have the value 0. Graph will look like this. This is not to scale because that's a 2, that's a 1. This area, of course, is 1. This area, of course, is 1 because if it's a density function, its area has to be 1. So all I'm doing is taking a density function that's slightly different from the original. So I'm making it as simple as I can and still be different. So I just made it look like a triangle instead of a straight line. Of course, it's going to make a difference in the answers, but you can see what's going on. So you have to figure out how to generate values of x2, where x2 comes from a population whose density function is this. Of course, if you understand the inverse transform method, that takes an instant. Not a big deal. But that's what you have to know how to do.
Shouldn't the graphs be non-decreasing?
This is a density function, not a distribution function. So to be a density function, the only requirement is that the function is never negative and that its total area is 1. Now, the distribution function is the integral of this density function. So you have to integrate this to get the distribution function, and then you have to use that in the inverse transform method. And that's another one of the stumbling blocks, it seems, because I can express a continuous random variable by its distribution function or its density function. You need the density function in order to calculate the mean and the variance. You need the distribution function in order to apply the inverse transform method. They're equivalent, but they're 2 different mathematical forms. Now, there's a tendency when in the final exam, if I give you the distribution function, then everybody will get the inverse transform method correct, but they'll calculate the mean and variance incorrectly because they always use the function I write down first. If I give them the density function, then they'll get the mean and variance correct, but they'll get the inverse transform method wrong. So you have to remember, there's a big F, there's a little f. Big F, it's not just that they look different, it's that the big F is a distribution function, the little f is a density function. They're equivalent, but they're 2 different mathematical forms, and they're used in for 2 different purposes. So whichever one I give you, then the question may require the answer from that, or it may require the answer from its equivalent. So don't make the mistake of simply taking whatever form I give you and plugging a number into that one. without asking whether or not what you're supposed to be plugging into is density or you're supposed to be plugging into distribution function. So it's very important to understand the difference between those two things. It's the second most important part of the course. No, third. The first thing is you have to be able to staple your homework on the upper left-hand side. And the second thing is you got to be able to pronounce and spell the word stochastic. You're there?
I lost that one.
You lost that one? Well, okay, but you got to, 5 or 6 weeks to get that before the final. Okay, so the question then is, how do I calculate the theoretical values of these things? So let me write that down. So can I, let's see, what did I erase? Okay, let me erase this. Everybody with it so far? Okay. What you have to see is two things. You have to understand what I'm saying. Hope. Okay, probability y equals 8. Let me rewrite that. And you should also understand what the purpose is, what the point is. Because part of the view of the course is that in engineering and in many and in science, many things, in fact everything, all variables, you could argue, are actually random variables. And so probability simply takes everything you've done in the past and allows it to be applicable to real life. Because if you artificially assume that everything is deterministic, then you're missing 90% of the world. And so the purpose of this course is to understand what you mean by saying something is random, how you describe randomness, and how you operate with randomness. And then everything you've done in the past is just a special case of what you're learning in this course. So now you're learning arithmetic. So the first half of the course, you learned what a number was. You learned how to count. And the second half, you learn how to add numbers. And that's as far as we're going to get in the course, is just adding up numbers. Okay, so let's see. Yes. What is it you have to answer here? So we've got these 4 cases. 1, 2, 3, 4. And for each of them, you have to calculate the expected value, the variance, and the probability that, except it's not x, it's made a mistake here. You want to calculate the expected value and the variance of now y, which is the sum of the x's. And the probability that y lies between 3.5 and 1.25, I keep forgetting those. Other way around. Okay, 2.5 and 1.35. And in each case, remember, there's theory and simulation. Theory, simulation. Theory, simulation. Okay, the simulation part is done. All you have to do is take what you did for homework 3 and add in this instruction which adds 2 of the x's and adds them up. And of the 4 cases done in homework 3, 3 of them are exactly the same and 1 of them is different. And the only difference here in terms of the simulation is writing the instruction that generates x's with that density function using the inverse transform method. Okay, so the simulation results are done. So the theory. So you got to calculate the expected value of the sum, the variance of the sum, and the probability of the sum. Now, as I've already indicated, although without proof, it turns out that to calculate the expected value and the variance if the random variables are independent is easy because the expected value of the sum is the sum of the expected values, whether or not the random variables are independent, and the variance of the sum is the sum of the variances if the random variables are independent, which they are in this example. So we'll illustrate the truth of those theorems. But the important thing is how you calculate this probability. Okay, so now I'll go back over here, and now comes the convolution stuff. Okay, so what we have is we have a random variable y which by definition is the sum of two random variables, x1 and x2. And presumably, we know the randomness of x1 and x2. That is, we know their density or distribution functions or probability mass functions, whatever it is. And based on that, we want to calculate the corresponding description of y. So, if these happen to be discrete, like with the dice, we don't need any big deal, because in fact we did it here. It's just common sense. All you're doing is adding up all possible combinations such that the sum is equal to whatever value you're trying to get. That gives you the probability mass function. But suppose that the random variables are not discrete, suppose they're continuous, then what do I do? So that's the question. So what I want to calculate is the distribution function of y evaluated at t. Once I get the distribution function, from that I can calculate the density function, and then I'm home free. Now the reason I want to work with distribution function is that distribution function has physical meaning. It's a probability. Density function is a probability only after you integrate it, after you take areas. So if I'm trying to derive things from a scientific, from an intuitive engineering point of view, physicist point of view, then it's usually easier to start talking about distribution function because that's a probability. Okay, so what do I want? I want to calculate the distribution function, which by definition is the probability that y is less than or equal to t. Okay, so this is simply definition. That's what distribution function means. What is that? Well, in our case, since y is x1 plus x2, I can rewrite this as the probability that x1 plus x2 is less than or equal to t. And by the way, my tendency is that when I'm talking in mathematical terms, I use subscripts. But when I'm talking in programming terms, I would write that as x with a big one because there's no subscript. So that's how you can, if you look through the notes, that's a distinction there. So I'm in mathematics land here. I have subscripts. Okay, so that's true. Now, what's the probability that x1 plus x2 is less than or equal to t? Well, now what I need to do is I need to sort of just follow my nose and see where it leads. So I'm going to rewrite this as the probability that x1 is less than or equal to t minus x2. So that's true, but I'm not sure how much it helps me because x2, remember, is a random variable. It's not a number, not a constant. So how can I calculate this probability? If this were a constant, then this probability would be the distribution function, capital F, of x1 evaluated at that value. But of course, what does that mean if that value is not a number, but if it is itself a random variable? So now I'm going to make the obvious step, which of course is obvious after I write it down, which is, now from the first part of the course, people are always saying, is this material cumulative? And the answer is, of course it's cumulative. That's like saying, if you're studying arithmetic and you get to calculus, is that cumulative? Do I have to remember what I learned in second grade, or can I forget that? And the answer is, no, you got to use what you learned in second grade in order to do calculus. Okay, so in the first part of the course, we had the theorem of total probability. So let me write it like this. This is equal to the probability that x1 is less than or equal to t minus x2 given x2 equals, I need more space here, equals probability x1 is less than or equal to t minus x2 given x2 is equal to u times the probability x2 is equal to u summed over all u. Of course, this doesn't really make any sense at the moment, because what's the probability that x2 is equal to u if x2 is a continuous random variable? It's 0, because there is no probability mass function for a continuous random variable. But am I thinking about it? I still think in this way by analogy. Okay, so let me write down here that this equal is theorem of total probability. Now you still don't really see why it is I wanted to write that. You can say, well, it looks like it makes sense, but So what? What's the point?
Yeah, wouldn't that come out to 0 then?
Well, I'm not done yet. Okay, I mean, there's a lot of steps here. Not a lot, a few steps. But what I'm trying to do is I'm trying to illustrate the thinking by which I'm going to get somewhere. And the problem is that I want to get rid of that x2 as a random variable. So what I'm going to do is I'm going to condition on it as being a specific value, which means that if I condition on it and multiply the probability of that condition and sum them up, then what I have is correct if I can use it. Now, if this, of course, is going to be a 0, it's not going to work. But what do you do with it? How do you go in terms of the analogous reasoning from discrete probability to continuous probability? What do you replace the probability mass function with? Well, let me do it, and you'll remember. The first thing I want to do is recognize that now, because of this statement that x2 is equal to u, I can rewrite that. I'm writing in all the steps here. This is now the probability that x1 is less than or equal to t minus u, given x2 is equal to u, times the probability x2 is equal to u. Okay, so in going from this step to this step, all I said is, if I know that x2 is equal to u, why don't I simply replace it by u? Okay, that looks a little bit better now because I've gotten rid of the x2 here. But I still have this condition right here. Okay, but now let me make one more assumption. The assumption that we're using for this problem, which is I'm going to assume x1 and x2 are independent. So this is going to simplify things quite a bit. Because if x1 and x2 are independent, then I can go around here and I can make one more step, which is I could say that the probability that x1 is less than or equal to t minus u, given x2 is equal to u, is the same as if I didn't know that x2 was equal to u, because that's what independence means. So I can drop this condition, and now it looks like this. Okay, so here's a distribution function. Because of independence, I know that the conditional probability given x2 is equal to u is the same as the unconditional probability. So in other words, it doesn't make any difference whether it's got the condition or not if the x's are independent. So I can replace this conditional probability by this unconditional probability, and now things are looking a lot better. Okay, now, of course I'm running out of space, so let me go over here. Right over here. Now notice, by the way, that this looks very much like this. It looks like a convolution because I have a sum of products, and in that sum, the argument add up to a constant. T minus u plus u adds up to t, that's that t. Over here, j, 8 minus j adds up to 8, there's the 8. So this is a convolution. Okay, what's the next step? I now have the probability that x1 is less than or equal to t minus u. That is the distribution function of x1 evaluated at t minus u. Okay, now we're getting somewhere. I couldn't do that here because x2 was a random variable. But here I can do it because t minus u is simply a constant, a number. So the probability that x1 is less than or equal to that is the distribution function of x1 evaluated at that. What's the probability that x2 is equal to u? Well, if it's a continuous random variable, that would be replaced by the density function of x2 evaluated at u du. And then I replace the sum by an integral. In other words, I integrate over all u from minus to plus infinity. And I'm done. Because I have the distribution function of the sum in terms of the distribution function and density function of the components of the sum. So now, all I got to do is plug into here and evaluate the integral. Okay, so let me erase this. Of course, I'm going to need it again shortly. And let's see where we are now. The distribution function of the sum of two independent random variables is the convolution of the distribution function of one of them, evaluated at t minus u, times the density function of the other one, evaluated at u du. But I didn't have to write it that way, because here I chose to put the x2 on the right-hand side, but I could have written this as x2, and that made that x1. In other words, I don't have to add up x1 plus x2. I could have added up x2 plus x1. So if I had done it the other way, then this integral would have looked like this. Would have been the integral of the distribution function of x2 evaluated at t minus u times the density function of x1 evaluated at u du. Notice, of course, that this t and that t are the same, and this u is a dummy variable. So again, following the rules of calculus, you've got to separate understand the difference between the dummy variable, or the index of summation, which is the u, and the argument which results from performing the calculation, which is the t. Now, it's kind of interesting, if you think about it, that what I just proved by the symmetry argument is that these two integrals are equal, regardless of what's inside of them. As long as that's a distribution function, and that's a density function, and conversely here, then it doesn't matter what distribution function or what density functions they are, they have to give the same answer, because x1 plus x2 has to be the same as x2 plus x1. So it's kind of remarkable that in probability, by using physical arguments, you can prove things that are complicated mathematically to prove. But just ask yourself, how would you prove that no matter what the f's are, if I put them in here and do this integration, I'm going to get the same answer? Okay, so we're right there for the moment, but I still have one more step. What I'd like to get is, I would like to get the density function of y. So how do I get a density function from the distribution function? How do I get the density function from the distribution function? What I'm trying to say, well, you take the derivative of the distribution function. Which means I have to take the derivative of this or this, it doesn't matter. So I'll use this one first. That's the derivative with respect to t of the integral from minus to plus infinity of the distribution function of x1 evaluated at t minus u times the density function of x2 evaluated at u du. The next step is obvious. I'm going to interchange the order of operation of integral and differentiation. In other words, I'm going to move the differential operator inside the integral sign. So again, that's physically what you would expect you would be allowed to do. In mathematics, there are conditions under which it's okay to make this switch. But those conditions simply require that the stuff you're integrating has to be well behaved, and everything here is well behaved. These are all simple functions. They don't oscillate. They're all bounded, so everything is easy. So any rule that you would expect to be allowed to use, you can use. So the next step then is to rewrite this as the integral from minus to plus infinity of the derivative with respect to t of the distribution function of x1 evaluated at t minus u times the density function of x2 evaluated at u du. Okay, so density function is derivative of distribution function. There's the distribution function, so I differentiate that integral, but in order to differentiate the integral, I'm allowed to differentiate the integrand. So I've moved the differential operator inside, and I have to differentiate what's inside. There's some theorem that says I can do that. I forget what it is. Leibniz rule or something like that. Okay, and this is, of course, what you learned in calculus. Okay, now how do I take this derivative? Well, I'm differentiating with respect to t. The only t I have is right there. So that means that all I got to worry about is this thing right here. Now, the derivative of big F is little f, right? That's the definition. The derivative of a big F is a little f. That's the relationship between density and distribution function. Of course, instead of a t here, I have a t minus u, but that's just a simple application of the chain rule. And so the result is that when I differentiate this, I get the density function of x1 evaluated at t minus u. Right, remember, if I differentiate a function of a function, I take the derivative of the inside, which in this case is 1, multiplied by the derivative of the function, which goes from big F to little f, and then I have the same argument. So this is the chain rule right here. Right, you all use the chain rule a zillion times when you differentiated things like exponentials and sines and cosines. So that's the chain rule. This thing here is Leibniz rule. That's the one that says that you can interchange the order of operation of differentiation and integration. Okay, so where are we? What is the final result? The final result is that the density function of y is the convolution of the density function of x1 with the density function of x2. There's the density function of y. How do I get it? I take the convolution of the density functions of the components. Now, notice that this looks a lot like this. In fact, you could argue by analogy, it's almost the same thing. Because the 8 minus j, the probability mass function there, is sort of analogous to the density function of t minus u. The j here is analogous, this is analogous to the density function of x2, u. So I replace j by u, and then I replace sum by integral. And so this and this have the same form. So this is also a convolution. And in fact, you've already seen this, because you did this in homework 0. Because in homework 0, what I did was I gave you the f's that are in here, and I asked you to evaluate this integral, which I called a convolution, but I didn't say why you wanted to do it. So in fact, you've already done this work here for the first two cases in the homework, because that was already done in homework 0. And I said at the time, what you wanted to do then was you wanted to get the calculations out of the way so you could worry about the understanding. Okay, so let's go back over to here. Here are my two random variables, and they're independent. And in that case, I can say that the density function, I'm just copying over now from that board, the density function of the sum is equal to the convolution of the density functions of the two pieces. And of course, again, by the same argument I made over here, I could interchange the x1 and x2. So if I had differentiated this one instead of this one, then I would have gotten this form. Integral from minus to plus infinity of the density function of x2 evaluated at u times the density function of x1, t minus u. x2 evaluated at t minus u, density function of x1 evaluated at u, du. Now, if both x1 and x2 come from the same population, then these two things are exactly the same. But if they come from different populations, then the mathematical form is a little bit different, and if you want to evaluate it, you choose whichever one is most convenient. Okay? So, there's the density function. Here's the distribution function. So those are our hot formulas. What I did was I started with this, and then I differentiated that to get that. And in fact, the way I think about it is I don't have to go through all of these steps, because the way I think about it is I just write down this immediately. What's the probability that y is less than or equal to t? It's the probability that one of the random variables takes the value u, that's the density function times du, multiplied by the probability the other one is less than or equal to t minus u, summed over all u. So I had written out those steps in great detail, but those steps just reflect that thinking. So to me, this is a one-step derivation. And this is exactly the same thing. And then I go from here to here by simply replacing the big F by a little f, which is what I do when I differentiate. And that's all there is to it. Now in the book, this is very complicated. I'll give you the reference here. You want to go to page 432. So 432 is at the end of the book. And if you do that, you'll see that, let's see. Yeah, if you do that, you'll see that the derivation leading to this is much more complicated. And the reason is that the argument that I made, like when I replace probability mass function by a density function du, that's not mathematically rigorous reasoning. But of course, that's the reasoning that's behind all this. And also, the author doesn't want to assume that things are independent. He wants to assume they're not independent and then specialize to independence. So if you look at the treatment that's given in the book, it's very complicated. It involves Jacobian determinants and all of this kind of stuff. Very complicated. But if you look at the final result, you can see immediately that the final result comes directly from this idea of the theorem of total probability. Okay, same argument. The probability that the sum is less than t is equal to the probability that one of them takes a particular value, the other one is less than or equal to t minus that value, added up over all possible values. That's the whole thing. So if you understand this, you can cut through all the mathematics. I go from here to here by taking the derivative, and that's the end of it. I'm home free. Okay, now, okay, next step. Suppose I wanted to calculate the expected value of y. By the way, any questions about this so far? Because you don't have to remember the proof. You should be able to understand the proof if you look at it step by step. I wouldn't ask you to reproduce it. But you should understand it and you should be able to make calculations from it. And you've already made calculations from it because that's what you've done in homework 0, which you're going to repeat in this homework. Yeah, is that a question there?
Can you give us an example for the application of convolution?
For the what?
Application?
Yes, the example is homework 4.
A daily life application where, like, other than the Giles problem where we started out with?
Adding up anything. And when you say application, you're saying, suppose that anywhere in your life you decided you wanted to add up two things, two numbers, but the numbers were not deterministic numbers, they were random numbers. Right? Suppose that, suppose you have an elevator, and the elevator has a capacity of 400 pounds. And and two people are going to get in the elevator. And you want to know what's the probability that the two people's weights are more than 400 pounds. Well, you don't know what those people weigh. If they weigh on the average 180 pounds each, does that mean that their sum is going to be 360 pounds? Well, you might have gotten a fat person and a skinny person. You might have gotten two fat ones. You don't know. So if you were designing something like an let's not take an elevator, let's take an airplane. And the airplane has a certain capacity, and the capacity is going to be met by, you're going to put in a certain amount of fuel, and then you're going to put in all these people. You don't ask the people what they weigh before you put them in there, right? And then you're going to put in all their luggage. You know approximately what something this size weighs, but if all these people come with backpacks full of lead, it's not going to work. And then what you do is you ask for the probability that all these people and all the other stuff that you put in the plane is going to exceed the threshold. And then you leave yourself a little bit of margin of error. and hopefully it'll work. Hopefully you're just not going to have a plane where everybody's fat and carrying a lead briefcase. So in engineering, this is used all the time, except that at the elementary level, you ignore those things. But if you ignore them, you do at your own peril. I want to ride in an airplane by a guy, designed by a guy that knows all this stuff. Okay, so application or examples of the actual arithmetic, that's what homework 4 is about. And as I say, when we go over it, you'll see half of it's already been done in homework 0. Okay, so the trick here is to understand what it is that these things mean. Okay, what's the expected value of y? Well, from the formula, I take the values of y takes multiplied by the density function of y and integrate over all t. That's the definition. So that means if I want to calculate the expected value of y, what I have to do is I have to find this density function, which is this integral, and I have to put that integral in there, and then take the integral of the integral. That's pretty tough. And besides that, remember that this is only for 2 random variables, but suppose there were n random variables. In a convolution, I could do it recursively. I could take the sum of the first 2, take the result of that, take its convolution with the density function of the next one, and then take the result of that, take that convolution with the density function of the next one. So you can see that this could become difficult from a computational point of view, but then you'll see that there's some major theorems that say that it's not. So we're going to get to that, but this is the idea. Okay, so how do I do this? There's a lot of work. But then there's a theorem. So here it is, a major theorem, which I've already stated, and I said I couldn't prove it. Now you can see why, but it's intuitively obvious, which is that the expected value of a sum is a sum of the expected values. So in other words, I can replace this by the integral associated with the individual components. In other words, no convolution. Right? In other words, what I'm saying here is that the expected value of a sum is the sum of the expected values. So in homework 4, this will be easy, because when I ask you to calculate the expected value of the new random variable y, you don't have to calculate the expected value directly. All you have to do is add up the 2 expected values of the pieces that you already calculated in the previous homework, which was easy. Now, the same is true for the variance, at least if they're independent, which in our case they are. Okay, so in the book, if I have this right, this stuff here is on page 368. So this theorem, page 368. But something doesn't make sense here because this stuff is on page 432, and this follows after it. So I think maybe in the book this is only for the discrete case, I don't remember. Or maybe the author just said what the answer was and didn't prove it. Yes?
So it's a TF x1 and TF x1 for both, or is there...
Well, if they're the same random variable, if they have the same density function, then this and this are the same, so you're just multiplying by 2. If they're different, then well, as you'll see, for example, in the homework 4, in case number 3, there are 2 different populations. So you have to calculate the expected value from each of them and add them up. Now, one of them you've already done, and the other one is the new one. Okay, any questions about this? Okay, so now we can put this together, and let's do this for homework 4. So I can erase all this. In fact, I should erase it, and you never want it to darken your door again. So I'd like you to look back in the book on the pages that I referenced just to see how complicated this is if you do it in a rigorous way and try and understand the intuitive arguments, which are really simple. Okay, so here's the homework. We have 4 cases. So case number 1, we want the x's are going to be uniform 0, 1. We want to calculate the expected value of y, the variance of y, and the probability that y lies between 0.25 and 1.35. Or the other way around, I always forget. Okay, so what's the expected value going to be if y is equal to x1 plus x2, and in case number 1, you're sampling twice from a uniform distribution. So in theory, what's the expected value of y going to be? It's going to be 1, because you already calculated it for the case of an individual x. If x is uniform 0, 1, then the expected value of x is 1/2. You got that from homework 3. And in fact, you made the calculation in homework 0. So it's going to be 1/2 plus 1/2, or 1. What's the variance going to be? Well, you already calculated the variance in homework 3. It was 1/12. Is that right?
Right.
Okay. So it's going to be 1/12 plus 1/12, or 2/12, or 1/6. Okay, what's this probability? Now you have to find the density function of y and integrate it. But you already did that, right? Okay, let's go back to homework 0. In homework 0, what you did was you calculated the density function of y, which was given by this formula, which at that time you called g, because you didn't know what density functions were. And what it was the integral from minus to plus infinity of the density function of one of them evaluated t minus u. They don't really need a subscript here because they're both from the same population. The density function evaluated at u, du. So you already did this in homework 0. And you drew the graph. So here is 0, here's 1, here's 2, here is the density function of the sum. And if you remember, the triangle. Right? So in homework 0, you did all this work. Except that now you know why you did it. Now, what you want to find is this probability. So that's the integral from 0.25 to 1.35 of the density function of y, like so. So that says that's the area under this curve between 0.25 and 1.35. That area represents the probability that the sum of these two random variables will lie between that value and that value. But you already did that in homework 0. What was the answer? Anybody got a homework 0 in front of them? And you didn't even have to integrate, because all you had to do was find the area of that triangle, the area of that triangle, subtract from 1, and that gave you the remaining area. Okay, so who remembers what that number was? 0.7 something or other, if I remember right.
707?
Was it 707?
Is it down?
Nah, I think it was...
75?
Did anybody here do homework 0?
Looking for
What'd you get? Give me 3 decimal places. Somebody must have it. I hope you have it, because otherwise you got to recalculate.
7575.
Okay, that sounds familiar. All right, so I think that's the right number. You should look back on homework 0. But the point is that you've already done this work. So this case is already done, case number 1. Of course, you should know what you're doing here. But you don't have to know what you're doing in order to answer question number 1. But now you should look back on homework 0 and see what the point was of going through all of this grief in learning how to do convolution, because it lets you answer a question like this. And if you can't add up 2 random variables that are uniform between 0 and 1, which are like the simplest random variables that are not constant, then forget it, you're nowhere. But this is important stuff. Okay, let's do case number 2. That'll take an instant. Okay, so for case number 2, we have the expected value of y. Well, that's the sum of the expected values of the individual pieces. Each of them was 1/2. So once again, the answer is going to be 1. How about the variance of y? Well, the variance of each of them was 1/4. So the sum is going to be 1/4 plus 1/4, which is 1/2. What's the probability? Well, now you have to use the convolution. So we want the probability that y lies between 0.25 and 1.35. Now, you already, in homework 0, calculated that convolution. And if you remember, you got a curve that looked like this. Right? And this curve had a formula, which was, let's see, if I remember right, it was lambda squared t e to the minus lambda t. Is that right? Okay, and you want to evaluate this area between 0.25 and 1.35 for the specific case in which lambda is equal to 2. And you did that in homework 0. And you got a number. Right? You're supposed to use a calculator to do this. You could do it by parts. There's other tricky ways you could do it, but that's not important. You tell the calculator the density function, which is what you got by evaluating the convolution integral, and then you plug in the numbers. Anybody remember what the answer was? It was 0.6 something, I think. What was it?
0.6611.
0.6611? Does that sound familiar to you? Okay, I'm writing this down here. I'm hoping that's right, because I'm going on your word. This is a great responsibility. Okay. All right, so when you run the simulation, of course, you should get a value close to that. This should tell you that everything works. All right, I'll get back to this next time, because we've got 2 more cases to do. But you can see that this is, everything should start to hang together now. Okay, so we meet again on Thursday.